Good afternoon, everyone. Would like to start off by telling you how humbled we are to be here in Basili presenting our thesis defense. I'm John Gallab. I'm joined by my colleagues Hend, Martina, Mina, Abdullah, and Abdelwahab. Today, we're going to be presenting our thesis defense about the on-the-fly image compression. We are extremely honored to have done this research work under the supervision of Dr. Tamer ElBatt from our department, as well as engineer Youssef Hanna from Google. So without further ado, I'll start by discussing our table of content. So today, we'll be first discussing our problem statements, and then we'll very briefly, go over all the related works that we have used in our research. We'll discuss briefly the initial attempts, as well as our finalized architecture, the main contribution that we have in this research work. It's an overfitting shallow autoencoders approach. We'll discuss the architecture, the experiments results, as well as our limitations and our future work, and concluding with our empowerment outcome throughout this research. So, to start with, we need to first discuss our problem statement, also known as why should you care? So what we're doing here is compressing and serving images over the internet in near real time, or as the project is called, on the fly. Not only do we need to compress these images in real time, we have to have a good reconstruction quality. Not only good, superb reconstruction quality. And after getting these images over with a really good reconstruction quality, we need to decode and decompress these images on the client side without making any assumption about a GPU on the client side, mainly on a CPU, to make this research accessible for everyone. So, to discuss our motivation behind this problem statement, we basically address two issues over the internet. Images are prominently available over the internet, and one could claim that it is a majority of the data transmitted over the internet. So by actually compressing these images, we save two resources. The first resource is the bandwidth. So we save the bandwidth that's used when we compress these images before they are transferred over the internet. And our second resource that we care about is the storage space on the server side. By compressing these images in a proper format, we save this storage in advance. So now that we have provided our motivation, we'll start by going over our related works with Hend, discussing the classical approaches that have been done so far.
Okay, so first we're gonna discuss classical approaches. There are two types of compressions. There's lossy and lossless. Lossy compression omits the least relevant data to achieve compression, which results in a high compression rate at the expense of the degradation of the image or the data. Methods for lossy compression include scalar quantization, which is used in JPEG, and vector quantization. On the other hand, lossless compression keeps all the data for a perfect reconstruction of the image and maintains its quality, but this will obviously result in a low compression rate. Methods for lossless compression include entropy encoding and Huffman encoding, like others. So two algorithms of lossy compression are WebP and JPEG. WebP is one classical approach for image compression that is based on video compression techniques, and it performs well when used to compress lower resolution images. JPEG is another algorithm. It's a widely used compression technique to reduce file size greatly while still maintaining respectable image quality. It has several standards like JPEG LS and JPEG 2000. So WebP outperforms JPEG when used on low resolution images. However, when it's used on higher resolution, it results in low quality reconstruction at a high compression rate. And some of the drawbacks of lossy compression is that some details from the data is permanently deleted and cannot be brought back. So while classical techniques are fast at compressing images, they do not achieve a high reconstruction quality at higher compression rates. And this is mainly because it has a fixed coda. So next we'll be discussing non-classical approaches that utilize dynamic coda.
Thank you, Hend. And now for our non-classical image compression techniques, which is now the main research direction for which is now the main research direction for image compression, as it would achieve higher compression rates with better image reconstructions than classical approaches mentioned before. So now we have two techniques. Our first techniques. The first technique is principal component analysis, or PCA for short, which is a mathematical algorithm used for compression by reducing the dimensionality of data. It's one of the most popular compression techniques, and the PCA itself identifies directions called principal components, where the variation of the data is maximum to reduce data. And now for on the other hand, we have our machine learning equivalent of the PCA, which are autoencoders. They are mathematically similar to the PCA, and in addition, it can map non-linear processes. It attempts to reconstruct data by using two networks, an encoder and decoder. When the bottleneck between the two networks, the encoder and the decoder, has lower dimensions than the input, compression is achieved. And convolutional layers could be added to compress images. After that, we have two other techniques, recurrent neural networks, RNNs, which are used in image compression due to their ability to capture dependencies in data. And it is also used to perform variable rate encoding to images, meaning that one image can have different parts, and each part be compressed with a different ratios than the other. Finally, we have generative adversarial networks, or GANs for short. They are two networks trained in parallel as a generator, which attempts to compress images, and a discriminator that discriminates between the original and compressed image produced by the generator. And now Mina will talk.
Thank you, Abdelwahab. So we've done many attempts. Not all of them were successful, but all of them were insightful. So we will start with our discontinued approaches. These approaches contributed greatly to our progress and our eventually our successful approach. So in the first attempt, it was a context-based compression selector, which is basically a recommender system that chooses the right classical compression algorithm according to the serving context. This would have worked because in different serving contexts, you can have different trade-offs that may make different compression algorithms suitable for this exact serving context. But it didn't work because when we were working on it, we made some simplification assumptions that made it too simple, that it was unuseful, and if we made another complex alternative, it would have been intractable. So we had to pivot, and we went to the next approach, which is the deep learning approach. Deep learning approaches, specifically autoencoders, generalize well and have high compression rates. However, they also didn't work because in our case, we wanted to be in real time, and deep learning architectures overall take a lot of time, and they are slow for our case. So from these insights and from the literature, we came up with our approach, which is overfitting autoencoders. It relies on a simple yet powerful idea, which is in machine learning, overfitting is a problem. However, in our case, we made it our ally. So our main contributions in this approach are producing a CNN-based autoencoder that is capable of on-the-fly image compression, and consequently, we need to have higher results than other approaches, both in reconstruction quality and in compression rates. And since it's in real time, so on the client side, we need to decompress only on the CPU without any GPU assumption. We removed the bottleneck layer in conventional autoencoders to make it less to be shipped with the compressed images. We are also one of the first and one of the few people who use weighted loss function that suits our objective. Moreover, our final approach, contribution and main contribution, which is using overfitting as our ally. So what is the process by which we realize those contributions? If a user opens a web page, some images get selected for that user. So we overfit the shallow autoencoder on this very small subset of images. And after that, we ship the weights of the autoencoder with the compressed representation of these images to the client side. On the client side, we decompress the images on CPU with no GPU assumption. And after that, if the user opens a new web page, this process happens all over again. So next, we will talk about the specifics of the proposed architecture with my colleague Abdullah.
Okay, so as Mina has introduced our new architecture, we can see here how this architecture looks. First thing we have is the image. The input image is given to our model. It could be of a variable size, any size basically, and then we resize it to a fixed size. Then after resizing to a fixed size that we have experimented on and changed to depending on our use case, we then pass it into our encoder. Our encoder is made up of two building blocks, and they are similar. It's made up of a 3x3 convolutional layer with a stride length of 2, and then a relu activation function to add nonlinearity. Then we are able to create our bottleneck representation, which is basically the thing we ship into our clients and how compression is achieved. It is made, we produce n activation maps, and this n could be changed based on our use case and scenario. Then we have our decoder, which is basically the inverse of our encoder. And again, it is made up of two blocks, and then we're finally able to create our reconstructed image. As you can see here, these are all the hyperparameters that we have experimented on. We have tried each and every single one against each other, and then we have produced the best results. The hyperparameters we have experimented on are the number of images, the batch sizes, the number of epochs, the SSIM loss weight alpha, which I'll shortly show you, and the learning rate. So as you can see here, these are the equations that we needed and we used: the mean square error, the peak signal to noise ratio, and the SSIM. And then, as you can see here below, this is our loss function, which Mina has already said. We were one of the first people to use a weighted average of two metrics for our loss function, the mean square error and the SSIM. And basically, alpha here is the weight of the SSIM loss in our function, which is a hyperparameter that we change. So moving on, how is this model achieving our problem statement and solving it? So first thing, we have the shadow encoders can be overfitted in real time, which is approximately 7 seconds. However, I'd like to also add that this 7 seconds is based on our GPUs and our computing resources. Meaning if it's on a server side with more powerful computing resources, it could be even less. Then we have the shadow decoder, which can reconstruct images on the CPU without the need of a GPU. This basically means that we don't have assumptions that the client has a GPU, so meaning that basically any client could use our model. Then I'd like to add that this compression was achieved because of the use of the CNN, which have the feature of weight sharing and tying, which reduces the overall network weight size to be shipped with the images. So moving on with Martina and with the experimentation and results.
So before we talked about our results, we wanted to identify metrics in which we can evaluate our results and see if they fit our criteria. So we picked 5 image assessment metrics, including the mean square error, peak signal to noise ratio, the structural similarity, multi-structural similarity, and the compression rate. And what do these metrics essentially mean or indicate? For the mean square error, 0 indicates a perfect reconstruction for the image. And for the PSNR, it's a bunch of ranges. So from 0 to 40, it's a worst reconstruction. And from 40 to 80, it's a moderate. And then from 80 above, it's an excellent reconstruction. And for the SSIM and MSSIM, 1 indicates a perfect reconstruction. And for the compression ratio, it's out of percentage. So 100 is the best compression ratio. And then, and we also wanted to make sure that the metrics we calculated are not redundant. So we used the Pearson correlation matrix, and we've highlighted the main, results from the matrix. But we can see that all of the metrics we picked were relevant, and calculating all of them together was not redundant. So coming to our experiments, we have managed to perform 4,125 experiments. But we also decided to prune models that do not fit our criteria. So the criteria in question included any model that resulted in peak signal to noise ratio less than 40, and SSIM less than 0.7, and training or compression time that's higher than 10 seconds, because that defies the whole purpose of on the fly. And also we decided not to use regularization layers to force the overfitting of the model. And our results, we chose to, like, the best four results we've concluded were, first, that the fastest training time occurs at the lowest needed number of epochs at a batch size of 1. And the second result was that when we remove the fully connected layers and we use activation maps instead, we managed to reduce the weights of the model. And then for the third result, it was sort of like a trade-off. So the higher the number of images we use, the better reconstruction quality. But that resulted in a higher training time. Hence, we had to come to a compromise, which is the fourth result. And that compromise occurred at 64 images exactly, that gave us the best image quality and the least time. And finally, since our problem statement is on the fly, time constraints were very important to us. And we managed to successfully compress an image at 0.15 seconds, which is very, very close to real time. And we can see that all the GPU compression and decompression and CPU compression is in milliseconds, which is deemed to be negligible when it comes to on-the-fly compression. And we've talked about a lot of numbers. So we decided to show you a visual result of ours. So you can see on the slide some images, and some of them are the original images and some are reconstructed. But can you tell the difference of which is which? Probably you can't, because our results actually came up to be very, like, hardly distinguishable by the human eyes. And then we'll talk more about the image assessment when it comes to the numbers with John.
Thank you, Martina. So now that we have discussed the subjective assessment of your eyes, which could be possibly different than my eyes, we need to discuss a more objective assessment. And this objective assessment can only be based on numbers, and these numbers are the ones discussed in literature. So we have changed, as we have mentioned, the number of images that we overfit per model, and we got the best results at the 64 images per model. And we'd just like to highlight a few numbers that we have obtained. Here, as you can see, we get a peak signal to noise ratio of 71.6 decibels when we do this architecture and we do this implementation. Moreover, we get a 92.4% mean structural similarity. Multi-structural similarity. And this is really important to note that we're only optimizing our loss function on the mean square error and on the SSIM, and the good results that we get are actually on the peak signal to noise ratio and on the multi-structural similarity index, indicating that not only our results are good, they're also robust on this data set. And to mention, this was implemented on the open image data set provided by Google. And this is one of the most representative image data sets available online. But given that it's a novel approach, given that it's a new also data set, there wasn't many literature on it. So we have decided to take it one step further and get the old data sets that might not be representative of the internet, but are the de facto data sets in image compression. These data sets are the codec dataset, the ImageNet dataset, and the VSDS 500 dataset. And after performing the same exact line of experimentation on these datasets, we have found that we get a peak signal to noise ratio and SSIM and multi-structure similarity index are very similar to the ones that we have obtained by our first dataset. Not only that, statistically, the differences are insignificant. And by performing testing a hypothesis between these numbers and the numbers on the original dataset, we prove that our approach generalizes on these popular datasets as well as the original dataset that we have used. Not only that, but we have taken it one step further. We have listened to our comments, and we have decided to compare our approach with the JPEG approach. So we have made sure that we get the same compression rate as the ones that we use here, which is 33.5%. In the JPEG, there wasn't that fraction, so we have implemented the JPEG on a better compression rate than ours, 33%. And we have decided to generalize these metrics and actually test how good do we perform with the JPEG, which is the de facto right now over the internet. And we actually outperform the JPEG, even if it's slightly, but we still do outperform them. We get a better similarity index as well as a better multi-structure similarity index. We do get a lower peak signal to noise ratio, and we do get a little bit of a lower mean square error. But as we have mentioned, the peak signal to noise ratio is direct from the mean square error. So these are actually kind of redundant metrics. And we outperform them not in the pixel by pixel copy, but we outperform them in the structural similarity index. And the structural similarity index does not only take the specific values of each pixel, it takes the overall shape of the image, which is even more representative. And if you look at the cosine similarity index, despite that sometimes it's considered obsolete, we actually get really good results. And it's fair to claim at this point that we might be the only researchers working on autoencoders that do outperform the JPEG at that aspect, given these image quality metrics. Just one thing that we have to pay really good attention to, that our architecture is really dependent on the number of bottleneck layers, the N. The N is very important, and if we do not select this N properly, we might get good reconstruction of the images, but we will not get a compression rate. So we have established the minimum image size that's required as a formula of the number of bottleneck layers. So given an image height H, width W, bottleneck number of maps N, count of images per model M, and the count of CNN layers C, and the stride per each CNN layer P, we can obtain this equation. And this equation is direct, as does not need any derivation. And by actually substituting with our numbers that we have used in the previous architecture, which we displayed its result to, we get that each image needs to be at least 256 kilobytes in order that we actually compress it. Irrespective of the image size, we are actually able to reconstruct it, and we reconstruct it really good, but we cannot compress it if its size is less than 256 kilobytes. As a matter of fact, this, as I mentioned, depends on the N itself, and given that it depends on the N itself, we can change the N dynamically as per the as per the smallest image per the batch itself. And this is a very reasonable number. I make this claim that images over the internet are getting better of a high quality right now, and 256 kilobytes are just negligible, and I'd say most of the images will pass this number easily. So we're finalizing our presentation. We're really sorry for taking long. To follow up with our limitations and final steps, we have a very strong limitation that I've just mentioned, that the bottleneck layer, the dimension itself is dependent on the size of the image. So it has to change as the image size itself changes. Moreover, we are attempting in the upcoming part to create a dynamic architecture that adapts according to this adapts the bottleneck dimension according to the original size. And we would like to find one final thing, or maybe someone else after us find it, which is the maximum depth that we can actually achieve, allowing for a timely CPU decompression as well as a good reconstruction. Our empowerment outcome, finally, we're really proud to have successfully managed to do that. We currently have an almost complete IEEE paper draft. We intend to submit it to the IEEE International Conference on Multimedia and Expo, the ICME for short. The ICME is going to take place in Toronto, Canada, hopefully, if we get through. Wish us the best of luck. It's supposed to be taking place on July 15th. We'll keep you updated on how it goes. So, to conclude, so far, we have implemented our architecture, an autoencoder that overfits the images. We do the actual reconstruction in a timely manner, much faster than any other deep learning architecture, and even a little bit better over the JPEG, which is the current de facto in the market. We'd like to thank you for your time, and we're open for questions right now.